In this course, we have already discussed many design considerations to predict and optimize the yield of PV systems. However, another very important feature of PV modules and PV systems is the reliability throughout its lifetime. A long lifetime and a high reliability of the system are required to enable low-cost solar electricity. Longer lifetime, less failure time, failure costs, maintenance time, maintenance cost, and minimal degradation all benefit the lower levelized cost of electricity by either increasing the lifetime energy yield or decreasing the lifetime costs of the system. Also, the interest and insurance rates depend on these key features. Lower risk results in lower interest and lower insurance costs. In this video, we will therefore discuss the reliability testing of PV modules. First, we will elaborate on the difference between actual field failure testing and laboratory testing. Next, the IEC certification standard is touched upon. Finally, we will discuss various laboratory reliability testing setups. Possibly the most accurate way to determine the long-term performance, reliability, and failure mechanisms is by actual outdoor performance data. However, good quality field data of PV system performance throughout its lifetime is limited. Additionally, generating field data takes many years. By the end of lifetime of the modules under test, the technology on the market might have already changed. Consequently, the results of the field tests might not be applicable to the current PV modules on the market. Currently, almost 85% of the 234 gigawatt of installed global PV capacity has been in the field for less than 5 years. Thus, it would require approximately 20 more years of data collection in the field to assess the reliability of the majority of today's installed PV capacity. Since investors would like to know the lifetime and the reliability of PV modules beforehand, various reliability tests have been developed. These tests accelerate the stress that the modules might endure during their lifetime. Hereby, we gain insight in the aging behavior of the equipment and in the failure mechanisms in a much shorter time frame. Most of these tests only require several weeks or months, depending on the test. This is relatively short compared to the expected lifetime of 25 years or more for PV modules. Unfortunately, with these lab results, it is still not possible to precisely predict the real lifetime performance. In many markets, PV modules are required to pass the IEC certification before these modules can be offered on the market. Thus, the IEC certificate ensures a minimum level of quality of the modules. The modules that pass the IEC qualification are less likely to have design flaws and thereby are more likely to endure outdoor operation. However, the qualification was designed to identify premature failure. Thus, this standard only tests if the modules pass a minimum requirement. It does not guarantee that it will last throughout its lifetime. Also, it does not predict a minimum lifetime of the modules. The IEC is a non-profit, non-governmental international standards organization that prepares and publishes international standards for all electrical and electronic technologies. There exist 3 different standards for PV modules. The type of standard that is applicable depends on the photovoltaic technology used. For crystalline silicon modules, the IEC 61215 is applicable. For thin film modules, the IEC 61646 is applicable, and for concentrated photovoltaic modules, the IEC 6218 is applicable. Let us now focus on the IEC 61215, which is applicable to crystalline silicon modules. The qualification includes a set of well-defined accelerated stress tests that aim to duplicate failure modes observed in the field. It is important that stress levels and the test durations are limited so that the tests can be completed within a reasonable amount of time and cost. The IEC 61215 prescribes a sequence of tests and criteria that have to be met after testing. There are a number of criteria that are checked visually. Also, the module's maximum power at STC is checked and compared to the value prior to the test. Furthermore, the modules should meet two electrical safety test requirements, namely the insulation test and the wet leakage current test. The IEC 61215 has, however, its limitations. As the qualification was designed to identify premature failure, it does not test for a number of common potential causes of failure. For example, resilience to potential induced degradation is not tested by this standard. Furthermore, certification testing is performed only on a small number of samples. Also, the manufacturer is free to select the modules it sends for testing, so there is no random selection. Additionally, the IEC certification only functions as a pass-fail set of tests. It does not report the actual magnitude of degradation after the tests, nor does it seek to discern the root cause of performance loss. Here we list a number of reliability tests for which most are also prescribed by the IEC 61215 standard. The failure modes to be tested can be divided into climate, mechanical, radiation, and electrical failures. More specifically, there are multiple climate tests such as thermal, damp heat, and humidity freeze cycle tests. Next, there are the mechanical tests such as mechanical load test, or the so-called pressure tests, and the hail tests, also called the ice ball impact test. Other tests are, for example, UV, electrical insulation, and potential induced degradation tests. We will discuss all these tests in next lectures. There we will explain under which parameters the test is performed, what failure mechanisms it simulates, and what the pass or fail criteria are according to the IEC 61215 standard. Subsequently, we will show a couple of these machines that have been filmed at the Energy Research Center of the Netherlands.